here.
Sorry.
And, and essentially what we're doing is we are importing that maze information into like our algorithm. We're going to go ahead and set our start point. So we're going to go ahead and set our start point, and then we're going to go ahead and set our goal. And then I think that's what it looked like. And then we're going to go ahead and set our goal, and then we're just going to let the algorithm search for like the best path. Um, I didn't know the level. I didn't know what to expect from a level standpoint. So some of the coding is very like rudimentary. Like we're not building this from scratch because that would take way too long. But we're going to talk about the high level concepts, the search algorithm that's working. We're going to talk about how you do image processing, things like that. So as you can see, the algorithm is still going. Still going. It's going to take it a second because it's searching in two places right now, but the goal is up here.
So, Aaron, my suggestion is try to keep it low level because our workshops are novice to intermediate.
That's what I
So,
designed
so
for. So
yes,
that's
and there may even be some kids here.
Yeah,
Um,
that is exactly
yeah.
what I designed
Yes, Sierra, I
for.
can do that. Yeah, yeah. So absolutely.
So now we found our path, and as you can see, it's tracing it like it's basically we found our path and we're calculating it back. And this purple line would represent the path that our robot would take. Um, Now, in a perfect world, we'd be able to do something with like the Vex VR, but unfortunately, this is not a perfect world, and there would need to be a little bit more tweaking before I could like give you guys all that. But for now, I think this is a pretty cool concept to cover. And we'll have some breakout sessions. Let's see, we have something in the chat. Okay, yeah. Cool. But yeah, that's what we're planning on today. Um, do I have permission to go ahead and get started?
Absolutely. Absolutely.
Okay, guys. So I'm gonna go ahead and give you You know, I have a whole engineering degree and I can never get that right. The putting the Python or putting the PowerPoint full screen. So good afternoon, everybody. My name is Aaron Shepard. I am an engineer at NASA Goddard Space Flight Center, and today I'm going to be doing an intro to artificial intelligence using Python. This is going to be a very high-level introduction kind of thing, and we're not necessarily going to get into the weeds of the algorithms or how AI works, but instead I'm going to show you how we as engineers would look at AI, look at different components of it, and then combine it into a system that would allow us to achieve a certain goal. Um, so I always like to begin my lectures with a little comic, and this one is pretty funny to me. It is called The Circle of AI Life. And so in this panel, it's humanity researches AI, then humanity perfects AI, then AI perfects itself, then AI enslaves humanity. Hopefully that won't happen. But then a solar flare disables AI, and then humanity, we go back to the way we were thousands of years ago and we worship the sun god. And I think we just repeat the cycle over and over again. Um, the only reason why I chose this is because it was funny and it talked about artificial intelligence, and I figured that would fit the theme of today's lecture. So our learning objectives, one thing that we're going to talk about is what is artificial intelligence, and then we're going to talk about the specific components of an autonomous robotic system. So how do we leverage artificial intelligence and other things to create a system that would be able to think and act autonomously? Specifically within that, we're going to talk more about image processing and just the basics of how you do that. And in our breakout sessions, we're actually going to process our own images a little bit. And then, like I showed you, our final product will be able to look at a picture of a maze and then calculate the route through said maze. And with that, in addition to image processing, we're going to talk about path planning. And then, unfortunately, we're not going to be able to implement this in today, but we will talk briefly about control policy development. So once we have our path planned, like what do we actually do to turn that into things that the robot can understand as actions? Let's see. Oh, yep, that was TA's. Put your name TA in the front. Cool. All right, let's keep the show going. So before this class specifically, you are going to need some instance of Python. You're going to have Python installed, and if you have it just through like idle, if you have your own IDE, so like Anaconda, Spider, PyCharm, what's the other one? Eclipse, just any form of running Python. The next thing that you guys are going to need is this GitHub repository. It's going to contain all of the code for today's lecture. So what I will do is go ahead and just hit that control click for you. And I will paste the link to skip the verification. I will paste the link to the GitHub repository in the chat, so you guys can go ahead and download it. So the way that you would download the GitHub repo is you could clone it if you want to. I'm not really developing this. You don't have to make different branches. Like this is just a way for everybody to get the same folders. So you can go ahead and if you hit the download zip button, you can just download this repository and then extract it wherever. TAs, so your copy of the code is going to be located in the master file here, which is just going to be the TA's copy of the computer vision and then the A-star algorithm that we're running. Students, and please make sure to pay attention to this. So each breakout session has its own folder with its own programs because they're going to be slightly different. So for example, if we're in session 2, I need you guys to open up the folder in session 2 and actually run those programs and modify that code. And same with session 3 and session 4. So going back, I do believe actually, quick show of hands, who does not have Python installed on their computer right now? Show of hands, raised in the chat. All right, Tiara, I see you. Does anyone else not have Python installed? Okay.
Yeah, you may
Yeah.
want to just go through a quick, here's where you get Python and install it if you could. If you want to share the screen, yeah.
Actually, that was going to be our first breakout session, and we could actually do this one together if you would like. So for TAs, if you look in your TA slides, they show that they walk you through how to set everything up. So essentially, if you do not have Python 3 installed, then you're going to want to go to this website here, which is python.org/downloads. So once you download Python, oh, that's not the link. Hold on. Oh, it copied the image. My bad, y'all. So we're going to go ahead and just go to this website. And do chat. Where is the chat? There it is. So we're going to go to python.org/downloads, and then you are going to download Python for your system. Is anybody not on Windows? Is anybody on Mac or Linux? Raise your hand and let me know in the chat.
We got a Mac and we have but they have PyCharm. Jada has PyCharm. Chitika is on either Linux or Mac.
Okay, so for the people that don't have Python, that's the one those are the ones I'm concerned with. But if you have Python, go ahead and download it for your respective operating system. It's either going to be Windows or Mac. So the next question is, for those of you who have Python installed, do you have the ability to run pip, which allows you to like pull in packages?
I don't know if they know what that means, but okay.
If you have PyCharm, you should have pip.
Dwayne says yes.
Okay, cool. Because the one thing that we're going to need is we actually need pip because we have to install in a few libraries to get everything to work. So where is my Zoom? Oh, there it is. Not that. That is not what I want. So how about this Tierra? Can I get the link to the TA slides? You never got them. Yes, I will go post them on the Google Drive or on Google Drive real quick. Do, 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 do. Let's go to boom.
I think I put them in Google Drive already. They're in they're in our drive. Who asked for that?
Yeah, you want the slides for the PPX
Yeah.
to
Yeah,
uh
I put them in there already. Who was asking?
It was me, Chiatica. I'm not sure if I'm in the Google Drive or not. That might be the reason why. I didn't see it before, but I'll take a look at that right now.
I just sent it to you in a private message. Chiatica, you should be good to go.
All right, thank you.
yeah. And I'm sorry guys, because apparently they're like it's saved in a weird file format, OTA, whatever that is. But if not, I have the PPX, the PowerPoint one. All right. Okay. Can we handle getting access to the Google Drive? Yeah.
Oh, I thought it was public. Okay. Give me one second.
Yeah. Um, so now for the people that don't have Python installed, have you installed in Python? Let me know in the chat. Okay. Okay, cool. Great. Let's look at the drive.
So maybe when you have Python installed, put it in the chat so we'll know who we're waiting on. I know Naomi's still working. So
Yeah,
anyone still working, put still working in the chat so we'll know if you have Python installed.
yeah. Okay, yeah. The TA slides are right here. Cool. All right. So the next thing you want to do after you install in Python, is you're going to want to add Python to your system path. And what that will allow you to do is basically access pip. So to run Python in your system path, for the people installing Python, you guys are on Windows, correct?
Mhm.
Okay, great. Oh, thank God. Yes. I always get nervous because I'm like, all right, if you have to install it and you're on Mac, I'm not on Windows or I'm not on Mac and I don't know how to help you. So what we're going to do is we're going to go to this link here, control click. Now you should be able to run pip through the command line as long as you have Python as like your system in your system variable. So what you have to do is you have to go to the control panel. And then you go to system. Is this old? All right, you should be able to just click on the window button and type environmental variables. Yeah, edit system environmental variables. And then you want to go to the advanced, or you want to go to environmental variables and then do your path.
Okay, you're gonna have to
And
slow down now, Aaron. Doggone. You lost me
okay,
at the system.
okay, yeah,
Okay, you said system, environmental variables, system properties. Okay.
environmental variables. And then you're going to want to click on path here. And then you say edit. And then you want to locate where your Python scripts folder is. and then you just want to add your Python scripts to your path. And then you click OK. Is everyone good now?
Okay, so just to make clear, once we open up environmental variables, we're going to add a path to our scripts. Where did you get that link from?
Okay, so environmental variables is here. Then you see path. You click on path, and then you click edit. And then you have to locate where your Python scripts folder is.
Okay, I gotcha. Okay.
So it could be in your C drive. It could also be, mine got installed in a weird place. So I had to go to users, my name, app data, local, programs, Python, and then so on.
Okay. So let's take a beat for a minute because I have no idea where mine is. And then when everyone finds theirs, we'll move on. So it's the Python scripts that we're looking for. Okay.
Right. But if for the people that have Python already, I'm sure
they already know what theirs is. Yeah, I'm sure.
Yeah, they have. I don't think they need to do this because if they can use pip, you should be able to. But if not, go ahead, Jada, and just do what we're doing because then you can just use the Windows command line and I know it'll work. So what I'm saying is that like if I run the command line, I can make Python calls from it. So I can say pip and then it knows what to do. If you've already ran pip before, then ignore everything that I'm saying because you have what you need. Okay.
How does the chat look? TAs, make sure you're helping in the chat if there are any questions coming up.
Yeah, because I think we only had 2 people that needed to install Python, which is good. So Naomi, Tierra, what's your status? How are y'all looking? Okay.
Scripts is the end of your path, right? That's the last thing.
What'd you say?
Scripts is the last of your path, right?
Okay. Yep, the folder, it's just scripts.
Okie dokie. I'm finally there.
Okay, and then once you add it to your path, then you should be able to you can open a command window, you can open PowerShell, and if you type pip, then you will not get an error. So what I'm talking about is if I open my command prompt and then type pip, I get a bunch of things, but it doesn't say error.
Go back up. What were you on? I think I might be in the wrong directory. Oh, okay. Yeah, it's mad at me. Jerk. Okay, that's all right. I'll figure out what's wrong.
Okay. And then while we're figuring things out, okay, cool. While we're figuring things out, we can always take time to get people's systems up to speed. Like I figured this would happen. Okay, so now that we have, for everybody who has pip installed and you know how to run it, the next thing that we need to do is add the 2 libraries that we'll need for the workshop. And that is going to be Pygame and then Pillow. So the Pygame library is going to be what allows us to do the graphics for our AI algorithm, and then Pillow is what will allow us to do our image processing. So if you guys, for those of you who know how to use the Python installer package, and if you've worked in Python before, it comes up enough. So what you're going to do is type pip install, and then you want hello. You hit enter. And so in my case, it's already like, hey, you already have it. Cool. And the other library that you want to install, uh, you can install through Conda, but Pygame doesn't install well through Conda. I've tried that before, so I would really recommend pip because that's what I've tested on. Um, but if you want to look up how to install Pygame and Pillow through Conda, which is like the Anaconda environment, then go ahead. So the other library again that you need to install is Pygame. Did I do? Yeah, I did Pillow last time. So the next one you want to do is Pygame. So it's just pip install and then Pygame. And in this case, it says my requirement's already satisfied because I've used this before, or I've installed this before. So TAs and everyone else, if you have the two libraries installed, just give me a thumbs up and let me know in the chat. So Mac, you would do the same thing, which is you would have to add Python to your path. And I do believe I have a link to how to install this on Mac. Yeah, right here. So verify the installation process. So in Mac, you should be able to open up like a command and I think Python automatically adds itself to the path in Mac. So I don't think you have to do the crazy things with Windows.
Hey, Aaron, in order for it to recognize Pygame, did I have to install Pygame in the same folder as the scripts?
No. Once you install the library, it will find it in wherever location it's supposed to be.
Okay.
All right, so one of the TAs is good. Is anybody else good? Like if we get the majority of the class that's good, then we'll move on and then we can always get everyone else caught up later. But for Mac, if you just open up your terminal, then you should be able to run pip directly out of there. Can I put the link in the chat? Of course. Here you go. Okay, Naomi, you need help installing pip. So what we will do is I will give you the link because Naomi, you are on Windows, and if you're still having trouble by the first breakout session, then you can stay with me and we will get you figured out. Um, do, 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 do.
I
So
will
here's how,
say that
yeah.
my pip did not work until I went all the way down to the scripts directory. So just typing it directly in did not work for me. I had to go to that specific directory. If you understand
Oh,
what I'm saying.
yeah, that's weird. You should be able to call it from anywhere.
I understand. Yeah, I don't know why that happened, but okay. So that may be what's going on with Naomi as well.
Yeah. So here's how you install pip on Windows. The NumPy package is also needed. I thought NumPy came standard. I thought NumPy came standard in. Yeah, you're having issues installing Pygame on Anaconda. That's why I recommended going through pip because I use Anaconda and I remember having issues with that too. So
System settings.
will there be a link to this recording or slides? There should definitely be.
Yes,
Yes.
that's why I'm recording. Absolutely.
Yep. Because we understand computers don't like to behave, especially when we're in a class like this. All right. So show of hands, who has everything installed? Okay. No one has anything installed. I just want to make sure. Mhm. Okay, yeah. It's okay. We we definitely understand that. Like it that happens all the time. All right. So for the sake of time, I'm going to go ahead and move on. And when we get to our first breakout session, then we can continue to troubleshoot and get everyone caught up to speed. So now that we now that we've covered the software that we've needed, um, let's see.
Cyril has his hand up, Aaron.
Am I using Python idle app or Anaconda? I'm using Spider, which is Anaconda based, but the app that you run it out of doesn't matter as long as you have the libraries. Like if you're on idle and you run the code and you've got the right libraries, it'll be fine. Um, so let's go back to the slides and continue. So we've already covered that. So now let's move on to the AI and autonomous system section. And again, if everything isn't installed for you already, we will work to get you caught up during the breakout sessions. Um, so let's talk about what artificial intelligence is. And that is the demonstration of intelligence by machines instead of humans or other living organisms like animals, bacteria, etc. And there are multiple subfields of AI research, including things like reasoning, knowledge representation, natural learning, planning, language processing, perception, object manipulation. It really is just one of the most wide open and exciting fields in both computer science and computer engineering. It's a very, very fascinating topic. Um, and the reason why it's popular now is that we finally have the computing power to do these highly mathematical, highly statistical machine learning algorithms where you can take in a bunch of data, manipulate it, and spit out answers much faster than we could even 10, 20 years ago, which is why you're seeing such a rise in AI now. So the origins of artificial intelligence actually come from a science fiction novel, and this is called Rossum's Universal Robots. It was written in the 1920s. The author, it's not a novel, it's actually a play. And the author is Carol Shepard. And basically, if you've read it before, if you've heard about it, this is where like the rules of robotics came from, where it's like, hey, a robot can't harm somebody. It always has to obey its human. And so like a lot of things in real life, it first came up in like entertainment. So we have a question: is AI intelligent or just pull information from the internet? The answer is AI, to a degree, is intelligent, and that intelligence could be pulling information from the internet. So, for example, when we talk about our own intelligence, let's say that you ask me what a boat is, and I don't know what a boat is per se, but I have Google. So if I don't know what a boat is, I'm going to go off and teach myself by either reading a book or pulling the information off the internet, etc. And so that, by definition, is intelligence. It's the ability to basically infer knowledge based on initial information that's given to you. So AI is intelligent. However, that intelligence isn't just excluded to pulling information from the internet. It could be things like puzzle solving, where again, um, for example, if I'm trying to solve a maze, I'm looking in my head and thinking which paths can I go down and not get blocked, and what's the fastest path. So in that case, that is an example of AI being intelligent, but not pulling information from the internet. So to answer your question, it's intelligence, and that intelligence can include pulling information from the internet, but that also can mean something else as well. So where we were, okay. So again, we started seeing early concepts of artificial intelligence in the 1920s. And by the 1950s, we actually had visions and theories of how to achieve AI. So there were two competing theories at the time. One was symbolic AI, and the other was a connectionist approach. So with symbolic AI, whoops, did not mean to do that. There we go. Hold on, we have a question. Which IDE am I using? I'm using Spider myself. But you can use Python, you can use PyCharm, Idle, Spider, anything works as long as it can run Python. So by the 1950s, like I said, there were two schools of thoughts of how you could achieve AI. One was symbolic and the other was connectionist. And so with symbolic AI, what that means is that you're using computers to create symbolic representations of the world and systems that could reason with said world. So in this case, you want to think heuristic searches, where you're exploring the space of possibilities for an answer, which is funny because the concept of heuristics is going to come up later in the session, because the algorithm that we're running is actually a heuristic algorithm. And this was the predominant paradigm of AI research from the 1950s to the 1990s. Ironically, the AI algorithm that we're running was initially developed, I think, in the mid 60s. So that makes sense. Eventually, though, researchers began doubting that symbolic approaches could imitate all processes of human cognition, because, again, human cognition is a very complicated thing. So they developed sub-symbolic approaches such as artificial neural networks, which are really popular, and just really prevalent now, especially with things like data mining, image processing, etc. So the next school of thought of AI that began to develop a little bit later, but is now really taking off again because we now have the computing power to do it, is something called connectionism. And that's the principle that mental phenomenon can be described by interconnecting networks of simple and uniform units. This is modeled after the way that our brain works, actually, when you think about it, because our brain is this whole system, but it's comprised of individual neurons that fire information to each other over synapses, and depending on how those neurons fire, information, the way that those neurons fire dictate the way that information is propagated and validated within our brain. And so now we're trying to mimic that, and we're having a little bit more success doing that. And the rest of the slide just goes on to describe what I basically said, where you distribute signals activity via connections that can be represented numerically. And numbering, or in learning, is just modifying the strength and connections based on experiences. Again, this is what happens in our brain. Basically, the best way that I can describe it is you do math in one part of your brain, if you constantly do math problems, those neurons are constantly firing. And so that the strength of those connections is improving. And so you're getting better and better at math. So this approach is heavily based, like I said, in statistics and mathematical optimization. And one of the things that we're seeing is that the success of deep learning networks, especially within the past decade, have increased the popularity of this approach to the concept of artificial intelligence. So now that we've talked briefly about what AI is, let's talk about the three components of an autonomous robotics system. And if you've taken a Black and Robotics workshop before, I'm sure you've heard of it, but it's the three principles: sense, think, act. So sensing is you're perceiving the environment based on external sensors and devices. So this could be things like camera, radio, LiDAR, ultrasonic, IR, anything that is like looking at the outside world from the system and feeding information about the outside world back into the system. So the think portion of this is, again, making decisions based on the perceived environment from the sensor data. So for example, if I have a camera and I get a picture, now the system can look at the picture and scan it and begin to identify obstacles that are in the way, or begin to think, okay, what's the best path that I can take to get from the start to the end? So in our case, our think is going to be a path planning algorithm. In a lot of cases with robotic systems, the think is usually something related to path, either planning, obstacle avoidance, path altering, things like that. And then finally, the third concept is going to be act, which is how do you carry out those decisions? How do you execute them? So once we plan the path, what do we do to actually turn that plan into things that the robot can understand to actually move itself in three-dimensional space? So the basis of our problem today is essentially that our little robot here is going to be stuck in a maze. And we can't really do anything. We can't get it out ourselves, but we can teach itself how to get to the end of the maze. So this block right here represents where our robot is going to start. That block represents where our robot is going to end. And then these walls are just this a maze. So these are the paths that are blocked. So in this case, our sensing is we're going to take a picture of the maze from above the robot, and we're going to send that picture in for image processing. Then our think is going to be based off the image processing, based off the maze that the robot sees. It's going to plan its own way out. And we're going to use a specific algorithm called an A-star algorithm that's really good at doing this. And then finally, the act, which we won't get to cover today, or we won't go into deeply today, is how would we develop a control policy? So once we come up with a plan, how do we turn that plan into commands that our robot understands? So now that we've covered that, we kind of have a base plan for how we're going to approach the problem of getting our robot out of the maze. Let's talk a little bit about image processing and how it works, because just quick show of hands in the chat. Have you ever heard of something called like computer vision, deep vision, image processing? Like, have you heard of these things before? Okay, so does anybody want to come on, like actually unmute themselves and say like, okay, how do you think image processing works? Okay, sure, OpenCV. Yeah, you guys can actually like talk. You can unmute yourselves. Like I don't have a problem with that. Uh, So
Okay, so
anybody,
can I chime in?
yeah.
Okay, so for OpenCV, the way it works is more like when you have like a picture of a person or let's say a face, for example. So it's kind of like give you some gray and white patterns on that face. Then with that, it could be able to sense, okay, this is actually where the eyes is. then also check the nose and the mouth. So with that, it could then use that to recognize the face. There's actually a terminology they call it. I think it starts from H. I've forgotten the name actually. So there's a name they call it, but I've forgotten that name. It's H. Is it almost? I've forgotten though. It's by the man who brought it out. So it's a long time I did that particular task anyway. So that's just the way it works. So it's more use more like the gray, the shading, like the shading of the black and white to get that facial recognitions and can be able to detect, okay, who this person truly is based on the space between the nose and the eyes and the mouth and all those. So those
Yep.
are actually how it works. Yeah.
Yeah. So everybody, round of applause, Ciro. That was an awesome answer. Um, that is a that is a very interesting thing to do, especially when you're I don't know if you guys ever cut on like the cameras on your computers, but if you notice when you cut on your camera, it'll put a box right around your face because it can locate where your face is, even on the video stream. And that's because a video is just a series of pictures. So what it's doing is it's basically analyzing those pictures to find where your face is and identifying it and then drawing the box around it. Does anybody else want to chime in on how they think image processing works? Nobody? Okay.
I'll take somewhat of
Go for it.
yes, and some of it, but I'm assuming it has to have some trained images of what, classification of whatever the object is. So then when it's doing some form of matching against it, it's most likely using like some type of statistics to determine whether something is more highly likely to be that object that it's trying to match against.
Yeah, that's absolutely right. And basically, what you've essentially described is what you use an artificial neural network for. It's to train you train an artificial neural network against a set of data, and it will look for patterns within that data. And then when it gets out into the real world, like if I train a neural network on my face, I just give it like 1,000 pictures of me and it learns to recognize my face based on the way my eyes are spaced or my nose or whatever. Then when my camera cuts on, because of that training, it can see the same things and say, oh, that's Aaron right there. So, all right, before we continue on, does anybody want to tell me how this would work? Because again, what we're describing, what both you and Cyril described are very high level concepts, but does anybody know how this would work on like a lower level, like a lower simplified, like if I wanted to analyze a picture, how would I do it?
I could possibly chime in on this part.
Yeah.
I think, well, it's been a while since I've done it before, though, but I've done a good amount of image processing type of stuff back in the day. Um,
Mm.
but from what I recall a couple of years ago, I was saying, well, first of all, it's all just a bunch of algebra for the most part. So you're going to basically break down a photo into a bunch of matrices, into one big matrix, basically, which basically is just holding a bunch of color values that make up the photo, basically. So I guess, for example, like one thing I did way back when was like converting a photo from, color to black and white and how exactly you go about doing that. So basically all you're ending up doing is going to each individual pixel that is on that photo and then basically changing the color to, however you want it to be. So basically like in the lower level, you're just basically editing or analyzing each individual pixel in that photo. So the more high definition, like the better, like the more pixels are on the photo, the more computationally expensive it is. So the more work it's going to take to be able to edit it or do whatever you want to do. But if it's like some super blurry, grainy, like 5 by 5 pixel photo or whatever, it'll be pretty easy to do whatever you want to do with it. But then obviously it's harder to use other things. But but yeah, basically there's trade-offs obviously with how high quality the photo is in comparison to how fast or how easy you want to do certain things to the photo. But yeah, it basically always comes down to taking it down to individual pixels and analyzing those pixels for whatever you might want to do with it. So yeah.
Sweet. Yes. And that is exactly the answer that I was looking for. So let's talk
Yeah.
more.
So
Okay,
sorry.
go ahead.
So just in addition to what you said, so like in summary, it's more like having the RGB format into grayscale at the end of the day.
Yes, exactly.
Yes, a value of between 0 and 255, just to make sure each of the pixels are analyzed with numbers, because computer sees numbers, human beings sees pictures. Thank you.
Yeah. All right. So yes, you guys basically have described like the next couple of slides. So let's cover that, and then we're actually going to go into a little bit of image processing, especially if you guys have already got things set up. And you'll see what I'm talking about. So what is computer vision? That is essentially acquiring, processing, analyzing, and understanding digital images. The subdomains of computer vision, so things that you could use it for, scene reconstruction, object detection, tracking, object recognition, things like that. For today's purposes, we're actually going to be doing scene reconstruction, and we'll get into the nitty gritty of that a little bit later on. So first of all, let's talk about what a picture is actually made of, like on the lowest level. And so I heard it before from a couple of answers, but basically a picture is a series or a matrix of pixels. And what a pixel is for a digital image is that it's the smallest addressable element on like the display device. So if you're looking at a screen, a pixel is the smallest part of the screen that you can control, essentially. And so the way that pixels are laid out, for those who haven't worked with image processing before, typically your first pixel or the beginning of your matrix will be located in the top left-hand corner. And so the width of your pixel or the X element is going to extend out to the right. So if you see, like in this case, we have this picture is going to be 4 pixels wide, and then the height element is going to extend down from the first pixel. So that would be like, it's 4 pixels wide, and then it's got a height of 4 pixels. So it's going down to 4. Actually, no, this is 5. My bad. It's starting from 0. So essentially the first pixel in this matrix would be here. And if we're following the structure, the last pixel would be all the way to the right and all the way down. And if you notice, we start at 0 and we go to 24. So this means that there are 25 pixels in this image. And again, it is a 5 by 5 picture, which in the grand scheme of things, a 5 by 5 picture, like someone literally said a 5 by 5 picture, you're not going to get really good quality image off of that, but it's still something that you could work with. And again, because our computers only see things in ones and zeros, essentially a picture is a matrix, and inside that matrix is going to be a whole bunch of numbers. So going into more detail, so when we're specifically looking at colors, like pictures that have colors, in this case, each matrix or each pixel will have 3 addressable channels. And so those 3 addressable channels, one will represent how red the picture is, or how red the pixel is, I'm sorry. The second channel will represent how green the pixel is. And then the third channel will represent how blue the pixel is. And is there anybody who can tell me why we specifically choose to only have channels for red, green, and blue in a pixel? And you guys feel free to like come off a mute and say it. You don't have to put it in the chat.
I'm pretty sure it's because you can make all other color combinations with those 3 base colors, if I'm not mistaken.
Yes, red, green, and blue are called the primary colors. So if you guys remember from grade school art class, you can make just about any color from combining red, green, and blue somehow. So that's why a lot of times you use that to represent the color within a pixel. Now there are other things that you can do, such as HSV, like hue saturation value, that gives you much more nuance and resolution within the colors. But for simplicity's sake, and for today's lecture, we're just going to be focusing on red, green, and blue color images. So in this case, each pixel will have a channel, and each channel will contain a byte. And so the red channel has 1 byte, the blue channel has 1 byte, the green channel has 1 byte. And if you've ever like set colors in a pixel before, you notice that it's always like 25500 is red, 0, 255, 0 is blue, and then or green, and then 0, 0, 255 is blue. And basically 255 is the maximum amount of the highest value that you can have in the channel. So it would be like the most red, and 0 is no red. So when you combine colors, like let's say you wanted to get purple, then you would throw red to 255 and blue to 255, and then you would throw green to 0, and you would get a purple color. And so what this means is that when you're the matrix that you use, so if an image is a matrix of pixels, it's actually a three-dimensional matrix. So I want you to imagine, if we go back to this first image, or if we go back to this picture before, this is something called a two-dimensional matrix where it extends out in both X and Y. And this just represents basically this just represents the number of pixels themselves. However, if we're using a colored RGB image, you'll have a three-dimensional image. So if you notice there's an X, Y, but there's also a Z component, and each level of the Z component, so one level represents the red channel, the other level represents the green channel, and then the third level represents the blue channel. And so when you're trying to process data, when you are trying to look at images and analyze them, essentially what you're doing is you are breaking these, not even breaking the image down. You are looking at the pixel values of these images and either manipulating it or scanning it to look for a pattern, so that way you can locate whatever you're trying to locate in your image. So again, our RGB images are actually represented by three-dimensional matrices, and that is both a good thing because we have a way to do it, and also a bad thing because if you notice, instead of just having 9 values here, you have 27. And so when you're manipulating RGB images, it's really easy to have a lot of data in a little bit of space, and it makes it challenging to actually churn through all that data because there's so much of it. So now what we're going to do, and before we go into our breakout session, I just kind of wanted to show you what I was talking about. So let's say I'm actually going to run a little bit of image processing code here. So what we have is essentially a picture of the maze that our robot has to navigate. So this is the image that I'm going to feed into our processing algorithm, or that I'm going to feed into this little bit of code. And essentially what I'm going to do is import our image processing library, and then I'm going to open it and convert the PNG file to an RGB, which I think it takes away, because the PNG also has like header information and all this other stuff that we really don't care about. So I'm just converting it into like raw RGB pixel values. And then I'm going to show it on the screen. But then what I'm going to do is actually work through a for loop, and I'm going to go through each pixel. And basically what I'm saying is that if there's a red pixel, we're going to turn it green. So if you notice the first value of X, which would be like, basically, since this is a three-dimensional array, I need 2 for loops, and then I need to manipulate something at the end of the second for loop. And so if the first value is greater than 200 and the next 2 values are greater than 1 or less than 150, I'm assuming that they're going to be red pretty much because, again, our original image only has like red and white in it. I think it has black in it too. So I'm making some pretty big assumptions based off the original image, but that's okay. And essentially what I'm going to do here is basically say, hey, if it's a red pixel, turn it green. And this is just a quick thing to show you again how image processing is done, where again, we're scanning through certain pixels and looking for things and either noting them or changing them to something that we want. So if I run this code, if you notice, it opens up a copy of the maze. And then in a few seconds, it has now opened up a copy of the maze, but then it turned everything that was red is now green. And so when you're talking about image processing and image manipulation, and when you're doing Photoshop, this is essentially what you're doing. Now, granted, there are more sophisticated algorithms and ways to do this that are faster and more efficient. But for the sake of today's class, I just wanted to show you the concept of, hey, like you can go into an image and manipulate the pixels and get something completely different, which I don't know about y'all, but I think that that is super cool. And that is going to be a fundamental part of what we're doing is reading the pixels and either noting their value or changing them to something that we desire. It's actually, you guys, if you downloaded it, then the structure should be the same. Where's my GitHub? GitHub. Boop. So your files, again, are going to be, for each session, there's a folder labeled session 2, session 3, session 4, and you want to open, on your downloaded local copy, you want to open session 2 and like follow the instructions for the TA manual from that folder, if that makes sense.
Sorry, everyone. I hit the button too soon. Aaron's got to give you instructions.
I do. Okay. So basically I'm gonna take the screen over again. So what you guys hopefully did is you went to GitHub and you downloaded the folder. So you would go, you download the zip. And then once you download the zip, you would extract it wherever you extracted it. In my case, I'm just going to go ahead and extract it in my downloads. So we'll just do extract all, boom, boom, there. But basically, the folder that you need to go into will be the main folder. And then if you see students, session 2, we're in breakout session 2. So you would go there. And then you have the maze, so you don't have to touch that. And then you would open the CPU Vision intro file here. Yeah, what's that opening in Notepad? I need to open that in Spider. Edit with Spider. There we go. But essentially, this is every Python file that you need to work with will be in the corresponding sessions folder. Does that make sense to everyone?
Yeah,
that makes sense.
Okay, yeah, I try to make things like as easy as possible for everyone to understand. So like you don't have, like, I will explicitly put things where they need to be put, or like where they're easy to find. So for the TAs, if you look through your TA manual, it even says breakout. This is instructions on like how to lead them through the breakout session 2. And it, like, all the code that you need to put in will be right there, and everything that you're looking for, like questions to ask the students, things like that. Does that make sense?
Yeah.
Okay. Can I send you guys back off to your rooms? No?
Go for
I
it.
think so, yeah.
What do you want us to do with oh, so we're just following the instructions in the PowerPoint?
So each TA should have a copy of a TA guide, and they should be able to guide you on what to do. But so the file that in this case for session 2, there's only one Python file in the folder, and that is going to be the computer vision intro. So you go open that folder, and then your TA will tell you basically your TA will tell you what lines to write. In this case, the file is blank because it's a simple, just to show you how image processing works thing. So they'll be able to guide you through on what lines to write. And for TAs, again, write everything as you see it in order. So I really do try to make this easy, y'all. Of course, if you guys would feel more comfortable, we can all do it together, and I can throw it up on the screen, so that way there would be less confusion. It's really your call. Like I can do it either way. I just want whatever is going to make sense for the class.
So Crystal,
Okay.
I put Crystal, I think Crystal just got here, so I'll put Crystal with Aaron. We need to have at least a little breakout for Naomi and Crystal, who need some help from Aaron with some stuff. And then we can come back to the main room if you want.
Yeah.
If that works.
So let's break out. Let's break out for 10 minutes and come. Can you set it to 10?
I'll set it for 10 minutes and then we'll come back just to get everybody onto the same page.
Yeah.
And then we'll come back in 10 minutes. Okay, I'm doing a 10-minute breakout.
Okay.
You may have to call out on the TAs if nobody says anything.
We're trying. We're trying.
We're trying. We're trying.
Are you guys, is it getting everything installed or is it actually?
Everything on my end is installed. I went through with serial with the brief, like the snippet of code. I'm just trying to run it to see if it's actually about to compile and then see what happens from there. But that's where I'm at.
Yeah. So with everybody in, is anybody having like installation issues? Because we got Naomi and Crystal. I'm so sorry. My dog is barking. I've totally blanked. But if anybody's having installation issues, just say so in the chat, and then we can pull you out in the next session and get you set up. But to show you what was supposed to happen, I'm going to take over my screen. Can you guys see my screen?
Yes.
Okay. So essentially what we were going to do is, do I have it here? Yes. Sweet. So if we're in session 2 and we're in the student session 2, basically that did not open. Here, I've got to edit that with Spider. My bad, y'all. All right, so for the CPU session, the first thing that we're going to do is essentially we're going to import in the libraries that we've installed. So we're going to import, and don't mind me, I'm going to have to cheat a bit. Okay, yeah. So we're going to say from PIL import image. That's our image library. The next one is going to be, we actually didn't need this one, but it's still there. Iter tools. That was actually needed later. Import product. And then the third one is import NumPy. I believe NumPy comes standard. If it doesn't, then just install it with pip, like pip install NumPy as in P. So the first thing that we're going to do is just read in our maze image and open it, just to show you like what's going on. And we're also going to print some dimensional information about it. So like, how big it is, things like that. So the first thing that we're going to do is create an object of the image class, and we will call this IM. And then we will say that is equal to image.open. Why do I have that? And then our picture name is just maze.png. And then we're going to, for now, we're going to convert it to RGB.convert. Is convert capitalized? Yep. And then we're going to say, nope, that needs to go here, .convert. And then we're going to say RGB. And that will close it. And then we're just going to pull like the size of the image. So we're going to say WH, which remember width is like the X direction from the right. H is the Y direction going down. And that's going to be image.size. And then finally, we're going to print WH, or I had you guys print it because you can't see the variables unless you're using like certain IDEs. But in my case, we don't necessarily have to print it. I can just show you in the window what the value is supposed to be. So I'm going to clear out my variables. And then the next thing that we're going to do is we're going to do im.show. And essentially what im.show will do is it will show the image that after everything you've done to the image, it will show it. And oops, there were some comments here that needs to get deleted. I hope that didn't throw you guys off. My bad. So with that, like we click run. I think I misspelled. Oh, iter tools, not inner tools, but we don't actually need this right now. So I'm going to cut that out entirely. And then the other thing is, whoopsies, that is a, wait, no, you should be able to call that like this. Hold on, let me see. Oh, tuple is not callable. So the other mistake is you have to put a parentheses around the WH because of the data type that it is. Hopefully that, if you guys didn't figure that out, I'm also sorry. So, oh wait, no, that's not the issue. My bad, y'all. Image.size is a variable, not a function, so it's not callable. That's what the thing was saying to me. I knew I tested this. So here's the image that we're pulling in, and we can pull the width and the height information on it. So in this case, the width is 669, the height is 669. So it's a perfect square, which I didn't intend for it to be that way. It just came out. So that's cool. The next thing that we're going to talk about is, I was going to have you guys, I had the TAs ask you, what do W and H represent? So can somebody tell me what W and H represent, even though I just said it like 5 seconds ago?
Like X and Y axis, same. Y we mean X and Y axis, we mean the W is the X, and that is the horizontal, and H is Y, which is the vertical length of.
Exactly. Exactly. Round of applause. That's exactly the answer that I was looking for. So now what we're going to do is we're going to start to see like why, how we can improve our image manipulation, or how we can actually manipulate the image. So now that we have this, let's go ahead and declare it. Let's make an array from this image so we can actually look at the individual pixels. And this is good because it makes sense to show it on my screen where you can actually see the variable values, and it definitely makes a lot of sense. So now we're going to declare an object called array, and then we're going to say that that is equal to numpy, which we have imported as np, and then we're going to say array. So it's going to be a numpy array of our image itself. And then, so let's see what happens when we do that. We show our image, and now we have an array. And if you notice, this array has 3 dimensions. It's 669, 669, and 3. And essentially what that is again, it's a 2x2, it's a 2-dimensional, or it's a 3-dimensional array. So these are the first 2 dimensions. It's a 669 square matrix. And then the third is, it means it goes up in the Z space 3 different things. And so if you were to look at that, and let's slice this, actually, yeah, so shape 669. So if we change our axis here, notice that this is the x-axis. This is the y-axis. But then if we look at it from the z-axis, we get, if I were to extend this out, this goes to 669 because we start at 0 and go to 668. And based on the slicing or the index of the z-axis, this tells you the RGB values. So in this case, since we're on the first index of the z-axis, this will actually represent all of the red values in the picture. So if you notice, we have a lot of red on the edge. It's screened at, it's just firing off at 255. Actually, no, that's probably white. No, that might be red. But because keep in mind, like the color white actually represents all the colors. Like it's all the colors at maximum value. So to make white, you set everything to 255, and to make black, you set everything to 0. So this represents, this index of the matrix represents the red values. If we go up an index, this is actually going to represent the blue values. And if you notice, there's a section, I mean, this is pretty much all white here because there's no blue in the image by itself. And then if we go up one more section, we slice it, this will actually, no, I'm sorry. This represents the green values. I get red, green, blue, and red, blue, green mixed up all the time. But this represents the blue values. which I bet you, or I'm sorry, this represents the green values, and then the next one will represent the blue. But I bet you if I go to a section, um, like I was trying to locate this section in the picture where it'd be all green, but it's kind of difficult to tell because again, you don't know where green is, you don't know where red is, you don't know where white is. So the question that I wanted the TAs to ask you is, I just wanted you guys to see, like, if you look at, does this data confuse you? Yes or no? Okay. No. Okay. Sierra, you get it. Like it makes sense. Uh, but the next question is, do you think that this is the most efficient way that we could process this image? Like, because if you notice, like, if we're processing this image, we have to check the red values, we have to check the blue values, we have to check the green values. Like, do you think that there is a better way to process this image that would be faster, less computationally expensive? Someone mentioned it earlier. Can someone come online and just give me an idea of how I could or how we could make this image processing easier?
Grace, Grayscale can do black and white image from the basic three primary colors. You make it
Ex-
easier.
yes, exactly. Everybody, a round of applause because that is the answer that I wanted you guys to come to when you looked at the image data was, wow, we have all these colors, but do we really even care that we have all these colors? The reason why I'm asking is because if you notice, our goal is just to navigate the maze. It's not to pick out any colors within the maze specifically. So if we can grayscale the image and then basically bias it so that way it's either black or white, that would give us much less data to process and it would make things happen much faster. So to grayscale the image, what we're going to do is we're going to change this line of code here. And instead of the convert, we're going to put L. And if I put L in, whoops, my bad. If I put L in here, and I can't get L in here today, okay. If I put an L in here, that's going to grayscale the image. And so, and let me show you the difference in the data. So if you notice we named our array, like we have it named array. Now we're going to name this the gray array. So that way we can compare the difference in the data structure itself. So if we run this code, we have a grayscaled image. Whoop-de-doo. So if you notice, like, let's compare the data between the array and the gray array. Can somebody tell me a difference just looking at the data itself?
Well, it's now a 2D array instead of a 3D array because you're no longer dealing with red, green, and blue. It's just all the black and white now.
Exactly. So if we actually, that's the correct answer. So we basically took a dimension off of that array, which saves us so much data. Whoops, let me open that. So now, if you notice, we don't have to deal with like slicing it or looking at it in a weird way. We can just look at the raw data itself. And now we know like generally what's black and what's white. So is there anything else that we could do to make this even easier to process? TAs, I will give you a hint. It is in the manual.
Well, all you're really looking for is a notion of an obstructed square and a non-obstructed square. So you really are just interested in two choices.
Exactly. We're really only interested in it. For this case, like I don't care what color it is. I just need to know, is there something there? So it's either there or it's not. It's either 1 or it's 0. It's either black or it's white. So one thing that we can do to make this even easier is bias the grayscale image so that way instead of being kind of black and kind of white, because if you notice, gray is like a mix in between. And if we go back and we look at these values in our grayscale, like we have like 79, we have 255, we got 13. I really, we have values in the 100 here, so it's kind of black, kind of white. What we can do instead is we can just go ahead and bias this image so that way if it's below a certain threshold, it'll be white, or if it's above a certain threshold, it'll be white, and if it's below that threshold, it'll be black. And that again just makes it super easy to process, because if I show you our grayscale image here, let's keep an instance of our grayscale image up. So we have our color, we have our grayscale, and now we're going to bias this to be black and white. And so to do that, we are going to add something called a lambda function to our image. And what this lambda function is going to do is it will go through all of the data and basically say, look, if that data is above 150, we're going to set it to 255. And if it's 150 or below, we're going to set it to 0. You can play with this threshold on your own if you really wanted to, but 150 it worked and I was cool with it. So now to do that, to bias our data, I'm going to call on our image object, and we're going to say, we're going to actually look at the points of the image. So im.point. And then we're going to write our lambda function. So lam, yep, I'm glad Python can spell for me. And that's going to say x. And if you don't know what a lambda function is, feel free to Google it, but it's just a quick way to write functions in Python, rather than like your standard for this, in this, if this, do this, else this. Like, it's just a more efficient way to write it. So essentially what we're saying is we're going to look at every point in this image. And if that value is greater than 150, we're going to set it to 255. So we're going to set it to white. Otherwise, we're going to set it to 0, which would be black. So if I run this algorithm, or if I run this program one more time, you notice we have a solid black and white image now. So to compare, let's compare that between our grayscale image, which is kind of like and our solid black and white image. Now, if I'm a computer and I'm trying to process this, the image on the right, the image on the right is going to be much easier, because again, I'm only looking at two things. It's 1 or it's 0, yes or no, black or white. And so if you're doing any kind of image manipulation, image processing, and color is not necessary for your application, one of the things that they like, the first thing they recommend that you do is just to take out the color and save yourself the data. So hopefully, it seems like a lot of you guys have worked with this before, so you probably already know that. But for the people who have never worked with images and have done image processing, I hope this is a good first step. So that way like, oh, okay, well, if I'm looking at an image and color doesn't matter, just get rid of color and it'll make things go a lot faster. So with that being said, I'm going to try to get through the next section of the code, or the next section of the session, and then hopefully we can get to the really, really fun stuff. Yeah, this is a good first step. You've never done image processing. Thank you. Again, this is why I teach these classes, because I want you to at least know a little bit about it. And I try to make things as simple as possible. So moving forward, now we've completed that. Let's talk about path planning. Cyril, you probably already know this. Cyril's probably going to chomp at the bit to answer this, but Cyril, can you tell me an application where path planning is really important? What would we use path planning for?
Like for self-driving cars, because I know we use this for self-driving cars, because you can also use it for Rust-based robots to also try to get maybe from a source to a location. And yeah, so mostly self-driving autonomous vehicles actually use this a lot.
Yep. Yeah. Does anybody else have an idea? So we have self-driving cars, robots. Does anybody else want to chime in and think what we would use path planning for?
Yeah, probably for Google Maps, right?
Actually, yes. Not this algorithm, but yes, to a degree, Google. Actually, yes, exactly, Google Maps, because that's basically what Google Maps does. Ooh, I hate that it restarts me. All right, hold on. Let me get caught back up. Origins of AI, symbolic AI, yada yada. Don't care, don't care. Three components, don't care. Cool. All right, what is computer vision? Sorry, guys, getting caught back up. Breakout session. All right, path planning. So in case you can infer, basically what path planning is a computational problem to find a sequence of valid configurations that moves an object from a start point to a destination. So it is literally planning the path. The name is pretty descriptive. And so the reason why we do this is that it would allow autonomous systems like robots, drones, Google Maps to find the shortest and or most obstacle-free path from a start state to a goal state. Typically, to do this, you need at least a map of the environment, a start state, and a goal state. And there are different algorithms that you can use. So the one that we're going to use today is something called A star. There's also D star, which is, I think, a little similar to A star, but I found A star to be the best. And then an RRT, which is basically a rapid random expanding tree. This was the algorithm we were originally going to do in this class, but when I decided to have the robot solve a maze, A star is much easier and much more clear to implement. RRT is great for other things, and I think I have a slide on it. Yeah, so the RRT algorithm that we were originally going to use is essentially creates these random trees that branch off. So if you notice, this is our start state. You would set a goal state in the map, and then you would let the random tree essentially branch to it. And it's rapidly exploring random trees, so RRT. So what this algorithm is designed to do is effectively search non-convex high-dimensional spaces. So if your space has like a lot of curves and things like that, this is great for it. And basically, like I said, it builds a random space-filling tree, and then you use an open loop trajectory to basically go through. The tree will branch out. Eventually, it will find the path, and then eventually a branch of the tree will hit the goal state, and then it will back calculate the shortest path to the start state. So again, let's say that our goal state was here. Once the branch gets hit here, it will back calculate how to get to the start state, and that is the path that you want to take. So again, this is really good. However, I did not think that it was best for our scenario. One of the things that you have to think about when you're implementing any kind of AI algorithm is just what is the right tool to get the job done. Like I said, this is good for actually RRT would be something like Google Maps I wouldn't be surprised if Google Maps uses some form of this. Because if you notice, it's taking into account all these curves and little things like that. And these actually look like what roads would look like on the map. But for something that is more linear and more straightforward, like a maze where you're only going 4 directions, left, right, up, down, an A-star algorithm is going to be a little bit more effective. So the A-star algorithm, as you can see, we have our start point. What it's doing now is it's searching for the goal point, which is the red, and it's going around the obstacles. And then once it finds the goal point, it will, let me pause it when it finds the goal point. So we're searching, we're getting blocked, but then we're moving around, and then we back calculate a path. Whoops, my bad. So this is something, the A-star algorithm is a graph traversal and path search algorithm, and it is something called an informed search. So that means that it's looking at weights. It's formulated in terms of a weighted graph, which means basically it's looking at every node and it's calculating the distance from the start node and then the distance to the goal node, and it's optimizing for the shortest cost based on those two factors. So what this does is it'll basically maintain a tree of paths that originate from the start node, and then it'll keep extending that path one edge at a time until it reaches the goal node. And then after it reaches the goal node, it'll back calculate the most effective route from its search. So this is, remember when we talked about things being heuristic? So this is considered a heuristic algorithm because it's exploring the space of multiple possibilities and then optimizing hey, what's the best one? So the cons of this kind of algorithm is essentially space complexity. So every node that you generate gets stored in memory. So on a small thing like this, it's not a big deal. But if I'm trying to basically map something to the resolution that has thousands of nodes or tens of thousands of nodes, you can have a memory issue really quickly. And this algorithm, again, because it's heuristic, and by nature, it will be outperformed by algorithms that can pre-process the graph. So kind of instead of exploring all the possibilities or multiple possibilities, like if an algorithm can narrow down, if the algorithm has a good idea of what possibilities will work first, and then narrow down from that, it will outperform this one because this one has a wider search, if that makes sense. So let's talk more in depth about how the A-star algorithm works. Basically, at each iteration, the A-star algorithm will determine which path to extend, because remember, it's only extending one edge at a time based on the cost of that path. Or it's based on two things: the cost of the path. So again, that's going to be the distance from the start node itself, and then the estimated cost to extend the path all the way to the goal. And so that's represented by this equation, which is f of n, which is going to be your total cost, is going to be g of n plus h of n. So in this case, n represents the next node in the path. G of n is going to be basically the cost from the start, so distance from the start, and then h of n, which is the heuristic cost to the goal. Basically, what h of n is an estimation of that specific node. How long would it take to reach the goal just from that node? And there are different ways that you can do it. You can use like you can take a Euclidean approach. So use Pythagorean theorem and basically say like, hey, the node is here, the goal node is here, make a triangle, and then, a squared equals b squared plus c squared. There are also more refined ways to do it. And I believe the algorithm that we're using kind of takes a little bit more of a refined approach. It's not just using Pythagorean theorem to help you a bit more accurate, to account for like having to curve around obstacles, things like that. So typically when you implement an A-star algorithm, you're going to do something called a priority queue. And this will perform basically the repeated section of the minimum cost nodes to expand. Essentially what it's going to do is it will calculate, like out of all the nodes that it has so far, it will calculate the node with the lowest f of n and then remove it from the equation space and update the f cost values of the neighboring nodes. And then once you update the cost values of the neighboring nodes, it'll keep doing this and expanding until it removes the goal node, which means, because basically it's each time it's taking out the lowest node. So it's taking out the lowest node, putting it somewhere else. And if you take out the lowest node and eventually keep on taking it out till the goal node is the lowest node, that tends to optimize your search path. For this algorithm. So before we move on to breakout session number 2, I have a couple of questions. Do you guys want to go back into your breakout rooms, or do you want to stay together as a class?
I'm good with staying as a class.
Okay. Is anybody
because of the time and to achieve our goal?
Yeah, you're right. Though we have like quite limited time, so I think we can stay together because of the time management now.
Okay, yeah, that happens. That always happens. All right, so we're gonna stay together. All right, so guys, you guys can follow me. Essentially, what we're gonna do is for this section of the code, this section of the class, we're not actually going to be manipulating any code. I'm just gonna show you how this A-star algorithm is implemented. So if we go into our section 3 folder, it says the A-star intro, and then we have our maze, although I don't think we need our maze. I just threw it in there just because. So let's look at the A-star intro. And we're going to go ahead and get rid of the computer vision intro, the A-star, the image processing, things like that. So what is going on here? Essentially, let me just run it and then explain to you what's going on in the code as I run it. So in this case, we're going to hit run. No module name, CPU vision. Oh. Okay, we can just delete this line out. I will update your GitHub because you don't need this. And that just got thrown in there. Oh no. Okay, that's interesting. Okay. So tell you what, let's call an audible and then I will fix your guys's code and then resend it back out because I think something got copied that should not have gotten copied. So to call an audible, let's go ahead and we're just going to do the session 4 code, which actually, no, I can go to my master. Let's open this here. And again, I opened it with the wrong app. Edit with Spider. No, maze.png. What? Oh, okay. That's because I didn't throw it in the master. Okay, hold on for just a second. Let's go back. Let's go back. Students. Oh, come on. Session 2. Maze. Actually, no, I have everything here in this folder. Let's do that. Yeah, that's what I want. No, that's not what I want. Hold on, guys, because it's set to it's by default it opens in another app, and that's confusing me. Do. Oh, come on. Go away. Spider does not want to load. It is being silly, and I don't know why it is being silly. Probably a memory holdup. Here, let's free that. Free that. And but basically, so what I was going to do here is just show you how the algorithm works. And then I was also going to show you how we went ahead and integrated the image processing with the algorithm. So that way we could take a picture of the maze, throw that into our algorithm. So that way it knows where the boundaries are. And then we could, solve the maze essentially just by looking at the picture of it. Hold on.
So is this essentially like what Tesla does?
On a very basic fundamental scale, yes. But Tesla does a lot of things too that we don't do or that we're not going to do. For example, it's looking at a map, but then it's also looking at a map to get a general idea of its path, but then it's also looking at the road itself and changing its behavior based off the information that it sees. And I actually do talk about that in a later slide. Oh, there's Spider. Cool. Why isn't it showing up? Okay. Yeah, that'll work. All right. So this is basically if we had time, and you guys, let me see. I think your folder, I may have to modify your folders to because I think a bug got copied in by mistake. But essentially, so when we start our A-star algorithm, we're just given a grid. And the way that it works is if you left click, the first location that you left click will turn orange, and that will be your start point. The next location that you left click will turn like blue, and that will be your end point. And from there, the next locations that you click will be your obstacles. But to make it faster, you can hold down the mouse and drag it and essentially create an obstacle. Also, if you right click on a point, you will erase it, and then you'll be able to place it somewhere else. So if you notice, I moved the endpoint from here, I right click, I move the endpoint from there or to here. If you press the C button, that will clear the screen. And then from there, just to show you how the algorithm works, let's do a start point here, let's do an endpoint here, and then let's just create a little obstacle. Let's create a little barrier. So if you look through the TA manual, once you press enter, it will begin searching. So the green represents open nodes, the red represents closed nodes. And so what it's going to do is it's going to expand the open node till it finds the path, and then it's going to work its way back to the start node, calculating the lowest cost path, and it will highlight that path in purple. So you start at this blue point, and then if you follow this purple path, that'll take you back to your original start point. So here's the start point, here's the goal. Let me see. I cannot believe I really threw in that bug. Oh man. Let me look at, because I thought I tested that. What? Let's look at your session, session 3. Oh, I cannot believe that got copied in by mistake. Oh man, I'm so sorry, guys. But okay, so that essentially is your pathfinding algorithm. And so then the issue that we had is great. Well, that's great that we can do a start and end point, but how do we autonomously upload the maze onto this algorithm? And so for your final session, which would be session 4, we actually have a second function, and it's called CPU. It's called like CPU computer vision. And what computer vision does is do CPU vision right here. No, it's going to open it. I really need to reset my default app for that. So what CPU vision is going to do is basically it's going to get the image data, and then it's going to take the maze, which if you remember is a picture, and then it's going to break that maze down into a grid that would match our algorithm here. So if I run this, hello. Oh, that's the wrong file. That's A star intro. This is A star. So if I run this algorithm, you notice that it creates a grid. Hold on for just a second. Let's restart the kernel. I'm getting impatient with it. It doesn't like me right now. Oh, and I'm running the wrong file. That's why. All right, so if you notice, this is a grid, but this image is not. So essentially, the way that you can import this maze onto our algorithm is to break down the maze into a grid, or basically, you break down the maze into a grid, and then you read the pixels to see if any pixel on the grid is going to be, since we turned this into black or white, if any pixel in like the grid space is black, then we set the whole grid to black. Or we mark the row and column of that grid, and then we can import that information into our algorithm. So essentially what happens is, and the way I have it set up in the code is that if you press the F key, you now have imported the maze onto your Pathfinder solver, or your Pathfinder. So if we look, this is our Pathfinder, and this is our maze. Now, there was one bug or one thing inherent to the design, because again, we turned everything black and white. And so the start and the end pads on the maze got marked as obstacles. But the way you can deal with that is you just unmark it as an obstacle. So you just hold that right click, and then you can erase the obstacle. And so then you have a complete recreation of the maze itself. This was here, and I do believe, yeah, I think there was a little gap here. Yeah, we'll just leave it. So now we have our gap, or now we have our maze set up. And essentially what this can do is we will set our start point. So we can set our start point right around here. We can set our end point right around here, which would match our maze. And then if we hit enter, it will begin searching for the path. And it's going to take it a while to solve it. Well, actually, if it didn't have to update these graphics, it would solve the maze like instantly.
And this is using A star?
Yeah, this is using A star.
Okay.
So if you guys, tell you guys what, give me about a day to, well, actually, no, I can just give you guys the working code, and then I can fix the master folder so that way it works all the time. And then you guys can play with it on your own to explore like how the algorithm is implemented. And then you can make changes if you wanted to. So if you notice, it's still solving. It's updating these edges, but now it's updating this one. I think it's about to finish because, oh, nope. You notice again, it's really checking all these possibilities. If it because you wanted to advance over here. There, now it found it, and now it's going to back calculate the path. Ooh, it froze. Joy. I guess it took too long. That's funny.
It looked like it finished.
Oh, it finished. Okay, cool. I guess it took Pygame just a second to update. So one interesting bug that I was going to have you guys work through is if we look at our computer vision, algorithm, basically, if you notice, I have the row set to Y index and the column set to X index. You would think intuitively it would be the other way around. So let's see what happens when I set the column and row to, like the row to X and the column to Y, like you would do normally. So let's run this program, and then let's run our algorithm again. And let's type in the F key to import in our maze. So can you tell me the difference between this maze, the maze that we generated, and the maze that is in the picture? Can somebody tell me that difference?
It's just rotated 90 degrees basically. So in terms of where the goal and start positions are, like the whole maze is rotated.
Right. So now, why do you think the maze would be rotated 90 degrees?
Maybe a 0, 0 starting point.
That's a solid idea, but that's not the direction I was looking for. Anybody else? What did I do in the code? Here, let's go back to our code where we're actually like enumerating and we're looking. This is the code where we are analyzing the maze with the Python image library. So you notice that row is X, but then column is Y. Even though like intuitively you would think the row would be X, but then the column would be Y, correct? So I know we're at 3 o'clock, so I want to wrap this up. Does anybody want to take a final guess before we wrap up for the day? Cyril, any of the TAs? Nobody?
No.
Okay. So,
well, you have the problem, right, that um, your XY coordinate graph system has the origin at the bottom left. Screens typically have them at the top left, and image file formats can be whatever they want.
Yeah. So, I'm going to go ahead and give it to you. It's an issue. It's not really an issue. It's something that it's inherent to the Python image library or the pillow that we imported. And essentially, the rows and columns are swapped. And so as you're iterating, if you're iterating, and actually I think it makes sense because as you're iterating through X, you're actually changing the column. And then as you iterate through Y, you're actually changing the row. So to fix this issue, you have to say like, if I'm looking at an index between Y and X, you actually want the row to be the Y index, and then you want the column to be the X index. It's just, again, if you work with the Python image library, you will quickly discover that things are turned around and swapped, and that's the best way to fix it, is to basically swap your X and your Y. So now if I run this algorithm again and wait for it to load and hit the F key, now the maze matches the orientation that we want. So here is what I'm going to do because we are at 3 o'clock and I want to be respectful of people's time. I'm going to go ahead and update the GitHub repo, and essentially I'm going to, if you guys want to try to fix the student section, you can, but I'm going to fix the bug in the master section, which is just it's missing the picture. And then, so now we're in the master section where it's missing the picture. If I close out this and then open this in the master section, give it a second. Oh, spider. Actually, let's run it again. We reload the module and see now our algorithm works. So basically I will modify the repository to have the TA instructions, and then it will have the fix in the master. And if you guys want to play around with the master, you can. If you want to try to fix the bugs in this, in the session ones, you can as well. They're pretty descriptive, especially if you're familiar with Python. And then from there, I will let you guys have at it. So let me go ahead and make this change really quickly. Let's go ahead, let's do master. And actually, yeah, I don't want to just sit here and waste your time. So before we wrap up for the day, does anybody have any questions? Nobody?
Your slide decks?
Yeah, I'll throw the slide decks in the GitHub as well.
Yeah, they'll be on the share folder and the GitHub. And also I'll put the recordings on video. And Bahi, I have a few lecture slides on YouTube about this. I'll email that to you too, about A* and search algorithms and stuff like that.
Can you send that as well to Dwayne?
Hey, I'll just send it to the group.
Yeah.
Yeah. I can also send you guys the documentation I followed for the Python image library. Let's see. So the master should have Yep, maze.png. So the bug in the master is fixed. I will let you guys fix the bugs in the student if you want. So you guys can go ahead and re-download the. You can go ahead and re-download the GitHub. We'll post that, and then I will also add a section for slides, so that way you guys can pull down the slides. But with that being said, let's see, do I have anything else in my slide deck? A-star algorithm. Yeah, that's all we had for today. Hopefully, if we continue on with this section, we can then talk about implementing a control policy. So do you guys mind if I talk for like 2 more minutes, and then I will give you guys the rest of your Sunday afternoon back?
I want you to add one thing to that talk. Tell us how this marries to Vex VR, because that's what I would love to be your next workshop.
So this marries to Vex VR essentially because what you can do is set Vex VR to have the robot be a maze, and then the next part of the workshop would be, once we've calculated the path, figuring out how we translate that into robot commands. So because if you notice, when we calculate a path, let me pull up what a path would look like on the slides.
Okay.
The TA slides. Yeah, there we go. Because essentially, when you pull up the path, you not only have to account for the direction, you not only have to account for the fact that the robot is moving, but you also have to account for the rotation of the robot, because in the path, the robot can't just move right on its own. You have to rotate it right and then move it forward. And so as you're doing that, you have to account for both the direction that the robot's heading in and ultimately its rotation.
Okay.
Let's do, and I figured that would be a bit much to include in one section.
Yeah, so that would be good for the next workshop.
Yeah. So looking here, you can see the purple path. Let me zoom in on it more. So if the robot is facing forward, it's fine. And basically, to calculate the distance that the robot needs to drive, you can just take the ratio of like the number of blocks to the distance on Vex VR, which I believe is like, it's 1,000 millimeter square or whatever. Something like that. So you can take the ratio of basically this image to this image and calculate the distance that you would have to move the robot for things to match. If you were doing this in real life, that's exactly what you would do. Like, for example, if this were a real maze, then I would take a ruler and sit it somewhere in the maze, take a picture, and then count the number of pixels that the ruler is, and that lets me know how many pixels is a foot.
Yeah.
So
this would be really cool to make an algorithm from what you just taught that solves one of the Vex VR mazes.
Yeah, that was the original goal. And then I was like, okay, it's gonna be a couple hours just explaining what's going on. But then the next goal again is to solve the Vex VR maze with it. So that will be the next workshop. So Dr. Berry, you have to invite me back.